By now, you should be comfortable using the differentialequations.jl package to solve both first-order ordinary differential equations and second-order ordinary differential equations. But so far, every example that we've seen has been a single differential equation. In some cases, a single differential equation is not sufficient to explain how something is changing over time. For more complex situations, you may encounter multiple differential equations that must be solved simultaneously. Having multiple related equations that must be solved simultaneously is known as a system of equations. How can we use the differentialequations.jl package to solve a system of differential equations? Well, let's find out. Welcome to Doggo.jl, where I explore the vast Julia wilderness and turn my discoveries into wholesome Julia tutorials. I'm assuming that you've watched the first 7 episodes of this series, so I'm assuming that you know how to use Pluto notebooks and that you know the basics of the Julia programming language. I'm also assuming that you know how to use the differentialequations.jl package in order to solve both first-order ordinary differential equations and second-order ordinary differential equations. With that said, let's get started. Let's start by firing up the Julia REPL and launching Pluto. Next, let's create a new notebook and title it Latka-Volterra Equations. This is optional, but I'm going to customize this user interface like I did in the first tutorial. Let's save this file by using the Save Notebook bar at the top. Just as a reference, I'm going to add a link to the Wikipedia article on the Latka-Volterra equations. Next, let's add a few packages. Now that everything's loaded, let's describe the problem that we're trying to solve. The Latka-Volterra equations are named after Alfred J. Latka and Vito Volterra. Latka was an American mathematician, physical chemist, and statistician. Vito Volterra was an Italian mathematician and physicist. Latka initially proposed the model in 1910 as an extension of the Verhulst equation, which I covered in episode 705. The Verhulst equation describes population growth that settles at some equilibrium level by following a logistic curve. But Latka went a step further by describing how population grows and declines and grows again in a cyclical pattern through an interaction between predators and prey. Interestingly, Volterra came up with the same set of equations that he published in 1926, completely independent of Latka, based on Volterra's research of predator and prey fish populations in the Adriatic Sea. Today, the equations are known as the Latka-Volterra equations. The Latka-Volterra equations are a pair of first-order ordinary differential equations. In math, when you have 2 or more finite simultaneous equations, this is known as a system of equations. In LaTeX, you can align equations on a specific character by using the ampersand immediately before the character that you want aligned. In this case, we're aligning the equations on the equal sign. So in the first equation, we're taking the derivative of x with respect to time. And in the second equation, we're taking the derivative of y with respect to time. But notice that there's an x and a y in both equations, so they're related in some way. The Latka-Volterra equations are also known as the predator-prey equations because they are frequently used to describe the dynamics of biological systems in which two species interact, one as a predator and the other as a prey. For this tutorial, we're going to try to recreate the simple example given in the Wikipedia article on the Latka-Volterra equations that show the population dynamics between baboons and cheetahs. Going back to the equations, the first equation describes the growth and decline of the prey, which in our example are the baboons. The second equation describes the growth and decline of the predators, which in our example are the cheetahs. Their derivatives define how the respective populations change over time. The Greek letters alpha, beta, gamma, and delta are all parameters that define either the growth rate or decline rate of the populations. We'll get into the meaning of each parameter a little later. So, we know how to solve a single ODE using the differential equations.jl package. But how do we solve more than one at a time? You'll be happy to learn that the differential equations.jl package can solve a system of differential equations. As an aside, in LaTeX, you can display a large opening curly bracket by using cases for multiple equations. Although this is technically accurate, subjectively speaking, this is a really ugly representation of the Latka-Volterra equations. But let's discuss. In order to solve a system of differential equations using the differential equations.jl package, you need to define a Julia function that takes the arguments du, u, p, and t. This is similar to the Julia function that we set up to solve a second-order ODE. But in this case, we're not taking the derivative of something twice. Instead, we're taking the first derivative of two separate but related equations. In order to keep track of everything, the differential equations.jl package uses index numbers, which we've seen before when using multiple parameters. So in this example, du1 is the same as dx dt, and du2 is the same as dy dt. Similarly, u1 is the same as x, and u2 is the same as y. The parameters are a little confusing because I'm numbering the parameters following the sequence of the first four letters of the Greek alphabet, which is alpha, beta, gamma, delta. So in this case, P1 is alpha, P2 is beta, P3 is gamma, and P4 is delta. We can clean up these equations when we define the Julia function. So that's a lot easier to read. Now that we've defined our Julia function, let's assign the variables. U is for the populations. Specifically, X is for the population of baboons, or the prey. We need to set the initial population. Let's bind the variable x_begin to a scrubbable Pluto UI widget, so we can change this value later. All of the default values that I'm using come from the Wikipedia article. Y is the population of cheetahs, or the predators. For the initial population, let's bind the variable y_begin to a scrubbable widget as well. Now that we have the initial populations, we need to place the values inside of a vector. Okay, let's move on to the parameters. Alpha is the baboon population growth rate. This growth rate represents any type of population growth, whether it's from natural births or due to immigration. Let's bind the variable alpha to a scrubbable widget. For the scrubbable widget, you can display a floating point number with 2 decimal points by using the keyword argument format followed by .2f in quotation marks. Beta is the baboon population decline rate. The decline rate represents any type of population decline, whether it's due to old age, predation, lack of food, or emigration. Gamma is the cheetah population decline rate. Since the cheetah is the predator, this decline rate represents population decline due to old age, lack of prey, or emigration. And delta is the cheetah population growth rate. This growth rate may be due to natural births or due to immigration. Now that we've set all of the parameters, we need to place the values inside of a vector. The only thing that's left is to assign values for the time. The example in the Wikipedia article doesn't provide a unit of measure for time, so I'm just going to assume that time is measured in years. Now that we've assigned the variables, we can define the problem for the differentialequations.jl package. You'll be happy to learn that you can use the ODE problem function to define a system of ODEs. And that's it. We are now ready to solve this problem. Like previous examples that you've seen, in order to solve this problem, all you need to do is use the solve function. Since our time span is 100 years, the solution keeps going. But for now, this is enough for us to look at. The value 1 column is for x, or the baboon population. The value 2 column is for y, or the cheetah population. As you can see, at time 0, both populations start at 10. But the baboon population immediately begins to decline very rapidly, while the cheetah population grows modestly at first, but eventually declines as well. Let's set up some variables to track the ending populations. It's a little difficult to get a sense of what's going on just by looking at these numbers. So let's plot it to see what it looks like. So the good news is that our plot looks identical to the plot in the Wikipedia article. But what does this plot tell us? The blue curve shows the baboon population over time, and the orange curve shows the cheetah population over time. Notice that they both start at 10, but the baboon population immediately begins to decline very rapidly. The cheetah population grows modestly at first, but eventually the cheetah population declines as well, presumably because all of the baboons are gone. But notice that as the cheetah population declines, the baboon population begins to re-emerge, presumably due to immigration, since the baboons sense that the area is now clear of predators. Without any cheetahs in the area, the population of the baboons explode, which in turn attracts cheetahs back to the area. As the population of the cheetahs increase, there's a rapid decrease in the baboon population. And on it goes in this cyclical pattern. Let's add some attributes to our plot recipe to help clarify this plot. Let's pull our widgets down so we can perform some analysis. There are a lot of widgets this time, so I'm going to fast forward through this part. Let's add some markdown so we can see the ending populations. This is going to be a challenge to see all of these widgets and the plot at the same time. So let's clean up this notebook a bit to make the display a little more compact. Let's start by creating a reset button. Now let's wrap the year slider inside of a begin end block so we can add the reset variable to this cell. For the initial populations, let's place this markdown on one line. You can copy and paste most of this code. In order to clear the error messages, we need to delete the original cells. We can do the same thing for all of the parameters. There's a link to my code in the description below. Again, in order to clear the error messages, we need to delete the original cells. Okay, let's hide some of these cells. Okay, that's a lot better. As you move the year slider, you can see both the plot and the values update for any time t. You can change the initial population for the baboons and or the cheetahs. Now, changing the parameters may lead to interesting results. Because there's a relationship between the predator and prey populations, changing the parameter of one will lead to population changes in the other. And of course, you can change all of these values however you like. Fun, right? Let's hit the reset button. Now, the Wikipedia article points out a caveat when using this model for real-world applications. Quote, for the specific choice of parameters, in each cycle, a baboon population is reduced to extremely low numbers, yet recovers, while the cheetah population remains sizable at the lowest baboon density. In real-life situations, however, chance fluctuations of the discrete numbers of individuals, as well as the family structure and life cycle of baboons, might cause the baboons to actually go extinct, and by consequence, the cheetahs as well. Unquote. So in summary, the Lotka-Volterra equations are useful for theoretical purposes. But as with any theory, be careful when applying them to real-world situations. With that said, these equations are still very useful for understanding population dynamics and have a long history of use in economic theory. Now before we go, let's take a look at a phase space plot. As you can see on this plot, this is a cyclical pattern, but these are not sine waves or cosine waves. Let's generate a phase space plot to see if that sheds any light on what we're looking at. For this plot, I'm placing the baboon population on the x-axis and the cheetah population on the y-axis. Again, you can find a link to my code in the description below. I added a semicolon at the end of the code to suppress the output, so we can add a dot to represent the baboon to cheetah population relationship at any time t. So this is an interesting shape. It's clearly not an ellipse. If you start at the lower left corner and move counterclockwise or anticlockwise, you can see that the baboon population grows rapidly when the cheetah population is low. But at some point, the presence of baboons attracts cheetahs to the area, and as a result, the baboon population decreases rapidly as the cheetah population increases. But then at some point, the baboon population is so low that the cheetah population plummets as well. And then the cycle repeats. Let's move the code for this plot above the widgets so we can see the impact on the phase space when we change the settings. Let's start with the year slider. So at year 0, the initial baboon population and the initial cheetah population are both 10. As we move forward in time, the dot follows a counterclockwise path around this phase space. During this time, the baboon population falls, and then rises, and then falls again. Also during this time, the cheetah population rises, then falls, then rises again. In this model, it takes somewhere between 14 and 15 years for the ending populations for both baboons and cheetahs to be 10 again. But as you can see, the baboon population is falling so rapidly at this stage that I can't get both populations at 10 on this plot. After that, the cycle repeats forever. You can see the impact on the shape of this phase space plot when changing the values for the initial populations and the parameters. Notice anything peculiar about this plot? This plot seems to be off, doesn't it? This is because our numerical solution is not very precise. by default, the differentialequations.jl package will select the fewest number of timestamps in order to find a solution, and then it will extrapolate the values in between the timestamps. You can increase the precision of the numerical solution by adding a couple of keyword arguments to the solve function for relative tolerance and absolute tolerance. This will increase the number of timestamps, thus making the solution more precise. Let's take another look at our phase space plots. You see, increasing the precision of the solution made a big difference on this plot. This plot looks a lot cleaner. Let's reset our model, and then let's break here to recap what we just learned. In today's tutorial, we learned how to solve a system of differential equations using the differentialequations.jl package. As a motivating example, we used the Latka-Volterra equations, also known as the predator-prey equations. The setup for this problem follows a similar workflow to solving a second-order ODE problem. So the Joule function takes the arguments du, u, p, and t. But the problem definition uses the ODE problem function, which is the same function that we use to solve a single first-order ODE. The solution returns multiple columns of values, one for each unknown function. Otherwise, the workflow is the same. One new thing that we learned is that we can increase the precision of the solution by adding a couple of keyword arguments to the solve function for the relative tolerance and for the absolute tolerance. As you can see, the differentialequations.jl package is a powerful package that can solve a wide range of problems. Pluto is also proving to be very capable of generating increasingly more sophisticated models. We still have a lot of challenging differential equation problems to tackle, so stay tuned for the next exciting episode. If you made it this far, congratulations! If you enjoyed this video and you feel like you learned something new, then please consider smashing that like button, leaving a comment, sharing this video, and subscribing to this channel. If you'd like to support the educational work that I'm doing, please consider making a purchase at the Doggo.jl online store. You can browse through a wide selection of Doggo.jl merch by clicking on the Store tab. For one-time donations, please consider using the Super Thanks button. For ongoing support, please consider joining and becoming a channel member. Channel members get early access to all of my new videos. Early access videos do not contain YouTube ads. New tutorials are posted on Sundays/Mondays. Thanks for watching, and good luck on your Julia journey.